it really makes you think, about the future of travel.
Yeah.
And the environmental cost of flying it's one of those big, like, naughty problems.
Yeah, it's a tough one.
Like, we all value the ability to connect with people and explore new places.
Yeah.
But the impact of jet fuel, all those missions, even the contrails,
Right.
it's substantial.
Yeah, it's really significant.
It's like, what, 5% of all human-caused climate change?
Around there. Yeah, it's a big chunk.
Okay, so let's dive into something that looks really promising today.
Okay. Yeah.
I've been looking at some really fascinating research and articles about this new technology out of Caltech.
Oh, interesting.
It's called a photothermocatalytic reactor.
Wow.
It sounds super complex, but what it does is actually pretty revolutionary.
Okay.
It's all about creating sustainable aviation fuel, or SAF, directly from sunlight and CO2.
Oh, wow.
Yeah.
Directly from sunlight and CO2. That's amazing.
Yeah. So for you listening, our goal today is to really get down into, like, how this thing works.
Right.
What makes it such a potential game changer?
Yeah.
And, could it really lead to greener air travel?
That's the big question.
Yes.
I think what's really fascinating here is this shift towards technologies that aren't just about, like making small improvements.
Yeah.
It's really about like fundamentally rethinking how we produce aviation fuel.
Exactly. And that brings us to the core of the problem, right?
Yeah.
We all know that, traditional jet fuel has a big environmental impact. But can we kind of dig a little deeper into what makes it so challenging?
Yeah, absolutely. I mean, beyond the obvious carbon dioxide emissions, which we know contribute to global warming,
right,
there's also the issue of contrails.
Oh, yeah, the contrail?
Yeah, those white lines you see in the sky behind airplanes.
Right.
And they can actually trap heat in the atmosphere. Yeah. And additionally, burning conventional jet fuel releases a bunch of pollutants that affect air quality, particularly around airports.
Makes sense.
So finding a cleaner alternative isn't just some, ideal.
Yeah.
It's a real necessity for both the planet and human health.
I totally agree. And that's where this Caltech reactor really enters the picture as like a potential solution.
Right.
So this multi-layered marvel, as it's been described.
Yeah.
Can you give us like a sense of its core design?
Sure.
And how it captures solar energy with such high efficiency?
Yeah. Think of it as like a very sophisticated, carefully constructed device that's meant to be like an exceptional solar energy harvester.
Okay.
At its base, there's this layer made of silicon and germanium. And these materials are particularly good at absorbing sunlight across a broad range of wavelengths.
Okay.
And then layered on top of that is a combination of gold and silver.
Gold and silver, wow.
Yeah, now this is clever. This layer excels at capturing infrared radiation and, crucially, like keeping the heat localized within the reactor. So above that, you've got a quartz window. And this isn't just ordinary glass. It allows about 98% of the sunlight to pass through.
Wow.
While minimizing the amount of heat that can escape.
That's amazing.
And finally, there's this vacuum insulation layer, much like, what you'd find in a high-quality thermos, to really trap that heat inside.
Okay.
So this entire design allows the reactor to reach operating temperatures between 120 and 249 degrees Celsius, using only sunlight.
Wow. Only sunlight. So, I mean, the brilliance here, as we see in the research, isn't just like layering these materials.
Yeah.
It's in the precise selection of, the silicon and germanium grabbing that broad spectrum.
Yeah.
While the gold-silver duo acts like a highly selective heat trap.
Yeah, exactly. It's like they work together in this really intricate way.
Yeah, it's really a fundamentally different approach to solar energy capture than we've seen before.
Absolutely.
I mean, one of the really compelling aspects is that unlike traditional concentrated solar power plants, which require these vast fields of mirrors and complex systems to track the sun,
right, yeah,
this reactor doesn't need any of that.
It's much simpler.
Yeah. And that simplicity leads to a significant cost advantage.
Yeah, exactly.
We're talking about like 40% lower infrastructure costs, which is huge.
Absolutely huge, especially when you're thinking about making this technology widespread.
Yeah. And get this. They've achieved 92% solar to thermal efficiency.
That's incredible.
Yeah. So that means almost all of the energy from the sunlight is converted directly into usable heat.
Very efficient.
Yeah. Plus, the modular design is key. Even small prototypes about the size of your hand.
Okay.
10 square centimeters.
Yeah.
They can be scaled up to much larger systems without any loss in performance.
Oh, that's really important for scalability.
Yeah, yeah. And under typical sunlight, they can reach 130 degrees Celsius. And with maximum sunshine, they've hit 249 degrees Celsius, all powered solely by the sun.
That's impressive.
No fossil fuels, no external electricity needed just to get it hot.
Right.
So we have this highly efficient way to generate heat from sunlight.
Yeah.
But then how does that heat actually get turned into, like, jet fuel?
Right. That's the next step. And that's where this process called ethylene oligomerization comes into play, right?
Exactly. So the heat generated by the reactor drives this chemical reaction known as ethylene oligomerization.
Okay.
Now, ethylene is a relatively simple molecule.
Right.
And oligomerization is essentially the process of linking these smaller molecules together to form longer chains.
Okay. I'm following.
Think of it like Legos.
Right.
Ethylene molecules are the small blocks. And oligomerization is the process of snapping them together, driven by the sun's heat.
Okay.
To create the longer chains.
Right.
Specifically those with 8 to 16 carbon atoms.
Yeah.
Which are like the main components of jet fuel. So what makes this especially sustainable is how they power this snapping together process.
Yeah.
They use something called solar thermal catalysis.
Right.
With zirconium-based catalysts.
Okay.
So the heat from the sun directly activates these catalysts, allowing the oligomerization to occur without needing energy from fossil fuels, which is, the conventional way.
Yeah, the traditional way this is often done in industry.
Yeah, exactly.
So to really understand the sustainability aspect, where does the ethylene itself come from in this closed loop system?
Right. That's a critical piece of the puzzle.
Yeah.
So to make this a truly circular carbon cycle, the ethylene is produced from CO2 electrolysis.
Okay.
Essentially, you take captured carbon dioxide and using electricity, ideally from renewable sources like wind or solar,
right,
you convert it into ethylene.
So the very CO2 that's a problem becomes the raw material for the fuel.
Exactly. And that creates a carbon-neutral feedstock,
yeah,
which is a significant step towards sustainability.
Absolutely.
Plus, the ethylene oligomerization reaction itself isn't some brand new experimental process.
Right.
It's already used in various industrial applications, which makes scaling up this Caltech technology more practical.
Yeah, it's not starting from scratch, which is helpful.
Yeah.
So the process sounds remarkably sustainable, but ultimately this fuel has to perform in an actual aircraft.
Right.
What can you tell us about the characteristics of this solar-derived SF?
Yeah, this is where, the rubber meets the runway, so to speak.
Yeah.
And it's really encouraging. The SAF produced by this reactor is designed to be a drop-in fuel.
Okay.
And this is huge for airlines.
Yeah.
Imagine just being able to swap out one type of fuel for another without having to redesign engines or overhaul their entire logistics.
Right. That would drastically lower the barrier to adoption.
Exactly. So drop-in means it matches conventional Jet A1 fuel in all the critical properties.
Okay.
So we're talking about energy density. It provides the same amount of power at 43 megajoules per kilogram. It also has excellent cold flow properties.
Right.
With a freeze point below negative 47 degrees Celsius.
Wow.
Which is, essential for safe operation at high altitudes.
Makes sense.
And perhaps most importantly, it's fully compatible with existing aircraft engines.
Wow.
And current fuel storage and distribution systems.
So airlines could theoretically start using this fuel tomorrow.
Yeah.
Without needing to make major infrastructure changes.
Exactly.
That drop-in compatibility is indeed a major advantage for widespread adoption.
Yeah.
But what about the feasibility of producing this fuel in, the massive quantities needed by the aviation industry?
Right. That's the big question, isn't it?
Yeah.
So researchers estimate that at a large scale of production, they could potentially produce SAF for around $2.50 to $3.50 per kilogram.
Okay.
Which puts it, in the same economic range as some conventional biofuels.
That's good, yeah.
Yeah, so there are some really interesting factors that could help with scalability. Because these reactors don't require, vast centralized solar farms with tracking systems.
Right.
There's the potential for more decentralized production.
Interesting.
So picture smaller reactor farms.
Okay.
Even on rooftops, maybe at regional airports.
Yeah.
Producing fuel locally.
Oh, that's interesting.
Plus, it's incredibly land efficient.
Right.
They estimate it could generate about 20 times more fuel per hectare compared to algae-based biofuels.
Wow. 20 times more.
Which have been, another promising area for SAF development.
Yeah, algae-based biofuels have been getting a lot of attention.
Yeah.
So this technology doesn't operate in isolation, does it?
No, it does not.
It seems like it could integrate well with other sustainability efforts.
Absolutely. And the modular design allows it to really work well with other green technologies. For example, it could be located near CO2 capture plants.
Oh, okay.
Using that captured CO2 directly as the feedstock for ethylene production.
Right, yeah.
And the electricity needed for converting that CO2 into ethylene could be supplied by nearby wind or solar farms.
So it's creating a really interconnected
Yeah.
and sustainable system.
Exactly. And the simulations they've conducted on larger scale versions of the reactor also show consistent temperature distribution.
Oh, okay.
Which is crucial for maintaining performance as the system grows.
That makes sense.
And the fact that the final fuel is already compatible with existing jet fuel infrastructure
Right.
just makes the transition much smoother.
Absolutely. So beyond just being carbon neutral in its ideal form, does this SAF offer any other environmental benefits that have been observed?
Yeah, and some of them are quite remarkable.
Okay.
And perhaps less immediately obvious. So trials using 100% of this type of SAF have shown a significant 26% reduction in the persistence of contrails.
Wow, 26% less persistent contrails.
Yes.
That's significant.
Yeah. And this is likely because the SAF produces fewer soot particles during combustion.
Okay.
And these soot particles act as the seeds for ice crystal formation in contrails.
Right.
So less persistent contrails means less of that heat trapping effect we discussed earlier.
Yeah, that makes sense.
They've also observed an impressive 85% decrease in ultrafine particulate emissions.
Wow, 85%.
Yeah.
That's huge.
Yeah, and this is a major win for air quality, especially around airports, where these tiny particles can have significant negative impacts on human health.
Yeah, that's a really important point.
Yeah.
And the potential for net negative emissions is a really exciting prospect.
Yeah.
Can you explain how that could be achieved?
Yeah, so this is where the true game-changing potential really lies, when you combine this technology with direct air capture, or DIC, which pulls CO2 directly from the atmosphere.
Right.
You're not just like avoiding adding more CO2.
Yeah.
You're actually actively removing existing CO2.
Oh, wow. Okay.
So researchers estimate that for every ton of SAF produced using DEET-derived CO2, about 1.8 tons of CO2 can be effectively sequestered.
Wow. So for every ton you produce, you're actually removing 1.8 tons from the atmosphere.
Yeah, that's the idea.
That's incredible.
This leads to a life cycle emissions reduction of anywhere from 70 to a full 100% compared to, traditional fossil jet fuel.
That's amazing.
Yeah. And furthermore, because this F contains fewer aromatic compounds, it burns more cleanly,
Okay.
resulting in lower emissions of other harmful pollutants around airports, not just CO2.
Right. Yeah. It all sounds incredibly promising, but surely there are still obstacles to overcome before we see this technology widely implemented.
Of course, yeah.
What are some of the main challenges on the horizon?
Absolutely. No technological breakthrough comes without its hurdles.
Right.
What the primary technical challenges is the durability of the catalyst.
Okay.
So the zirconium-based catalysts they're currently using have a lifespan of around 1,000 hours of operation. And for industrial applications to be truly economical, they'll need to extend that lifespan considerably.
Right. That makes sense.
Yeah, another challenge they're addressing is managing water vapor within the reactor
Okay.
to prevent it from interfering with the desired chemical reaction.
Right. Yeah. What's the Invention strategy for rolling out this technology on a global scale?
So the approach appears to be a step-by-step process.
Okay.
The initial phase involves establishing pilot plants, 10-megawatt demonstration units at strategically chosen sun-rich airports,
Yeah.
such as those in Dubai and Phoenix.
Makes sense.
The goal here is to test the technology in real-world operating conditions
Yeah.
and to further refine the processes.
Right.
Policy will also be critical. They're hoping for government incentives and the implementation of carbon credits for airlines that adopt SAF
Okay.
under international frameworks like ICOs, of CORSIA.
Right.
And finally, partnerships with airlines are essential.
Yeah.
The aim is to begin testing blends of this SAF with conventional jet fuel
Okay.
with major carriers as early as 2028.
Wow. So pretty soon.
Yeah, so it's also important to remember, as highlighted in our sources, that this decentralized approach really complements other solar fuel initiatives.
Right.
Such as the solar tower technology being developed at ETH Zurich.
Yeah.
Offering different solutions for different geographical and logistical contexts.
So to bring it all together, this photothermocatalytic reactor offers a truly compelling vision for the future of air travel.
Precisely. So the key takeaway for you, our listener, is that this isn't just another small step forward. It represents a potentially transformative pathway to achieving genuinely sustainable aviation.
Absolutely.
By directly harnessing the power of the sun.
Yeah.
And using CO2 as its primary ingredient, this technology offers a way to produce jet fuel with significant environmental benefits.
Yeah.
All while being designed to seamlessly integrate with our existing aviation infrastructure.
It's impressive.
So you now have a solid understanding of how this innovative technology works and why it could play a crucial role in shaping the future of flight.
This potential for modularity and decentralized production really makes you consider the wider implications beyond just aviation.
Absolutely. And that leads us to our final thought for you to ponder.
Okay.
Given the modular nature of this system and its potential for producing fuel in a more localized way, how might this technology reshape not only air travel, but also our broader energy infrastructure and regional development in the years ahead?
That's a great question.
What are the larger implications of our ability to directly harness solar energy to create such complex fuels?
Yeah.
And could this inspire similar breakthroughs in other energy-intensive sectors?
That's something to think about.
It's certainly a lot to think about as this exciting technology continues to evolve.
Absolutely.
So
fascinating stuff.
Yeah, it's really hopeful, I think.
It is.
Yeah.
It's good to end on a positive note.
It is, yeah.
Yeah. Thanks for having me.
Thanks for joining us.
Yeah.
And we'll see you next time.
See ya.